Hello, welcome to today's webinar, What's New and What's Coming in Converge, brought to you by Convergent Science. Thank you for joining us today for this new installment of our webinar series. My name is Scott Davis, and I am part of the business development team at Convergent Science. I will be your host for today's event. We're excited to showcase what's new and what's coming in CONVERGE CFD software. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD software used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Our speaker today is Keith Richards. Keith is a co-founder and co-owner of Convergent Science, and he is one of the principal developers of CONVERGE. His expertise includes numerical methods, detailed chemistry, engine intake flow simulations, rapid grid generation, and high-performance computing. Prior to co-founding Convergent Science, Keith studied intake flow modeling as a research assistant at the University of Wisconsin-Madison. Before turning the time over to Keith, I'd like to remind you, if you'd like to ask any questions during the webinar, please use the Ask a Question feature in your GoToWebinar. The time is now yours, Keith.
All right, thanks everyone for attending. So what you're going to see today in this presentation is based on a presentation that I give annually at our user conference. So it's a summary of what we have coming out in our latest version of CONVERGE, and also some of the new features beyond that we're doing some development on. So start off, I'm going to talk a little bit about our new versioning system that we have. We changed our numbering, our version numbering, to make it more consistent with industry standards. We've also got some updates in CONVERGE Studio that we'll talk about. Studio is our preprocessor, so we have some new preprocessing capability. Let's talk about some of the input and output changes and UDF changes as part of our code structure. Then we'll talk about chemistry and combustion updates, steady state. We put a lot of effort into our latest steady state solver. We'll talk about some embedding and AMR updates, changes to our solver, some FSI and multi-phase improvements. So first of all, let's get the boring stuff out of the way here, and that's the CONVERGE versioning. For those of you that are current CONVERGE users, this actually is relevant. I know this doesn't seem really cool, but this is going to be relevant going forward when talking about CONVERGE versioning numbers. So traditionally, the first two numbers in the version have been representative of the major release. So those of you who've been with us for a while are familiar with 2.3, 2.4, 3.0, 3.1. Those represent major releases. And the minor releases are represented by the third digit. With 3.0, we had a number of those. We've had almost 30 of the minor releases of version 3.0. And so that's that third digit. And those have been released fairly regularly, every other month or so for some of these versions. And then major releases have been released about every 2 years. So we've also had multiple versions that have been under active development and maintained simultaneously. We've had recently as many as 4 versions that were under development. The reason for that is we have customers that have been using older versions for some time. So the features that we would put in would get put into multiple versions, the current and the previous versions. So going forward, we are going to adhere to the semantic versioning standard. And I just want to state, what the semantic versioning standard is, and then explain how that's going to impact CONVERGE. So given a version number, major, minor, patch, those are the 3 digits. The major version is when you make incompatible API changes, which for CONVERGE means input file changes. The minor version is when you add functionality in a backward compatible manner. So we add new features, but it still doesn't break inputs. And then the patch version is when you make backward compatible bug fixes. So our intent is to have major releases more or less on an annual basis. And this is a significantly higher frequency than we've had in the past. We'll continue to support clients using older versions, but they won't be actively developed. So if you have projects that are continuing on using older versions, that's fine. You can still work with our support staff. We'll continue to support those, but we're not going to be actively putting new features into those older versions. So only 2 versions are going to be actively developed. We'll have our current development version, the one that we're working on for a future release, and we'll have the most current release version. Those are the only 2 that we'll be working on. So we're still going to make the development version available to clients. So we will have our latest stable release that will be the most recent fully supported version, but we are going to make that current development version that will become a future official release. We will make that available to you so you can have access to those features. So what all of this means here is that Converge 3.2, which we've had available as early access, this is officially going to be released as Converge 4. So going forward, we're going to be referring to that release with just the 1 digit. So we'll be talking about Converge 4, not 4.0. 4.0 is still meaningful, but when talking about that major release version, it's just going to be Converge 4. And that will be released early January. All right, so first of all, let's talk about some of the improvements we've got in Converge Studio. So we've added something that's called a custom panel creation. So this came from a customer request. They wanted to have a simplified version of Studio available for some of their users that were not hardcore CFD users. These are some people within the company that needed to be able to run CFD, but wanted to simplify the inputs and just limit those things they could change. So this has 2 versions. What you're seeing on the left is what an administrator would see. And the administrative mode is when you can add buttons, you can add fields, you can add scripts, and all of that is then going to be made available in operator mode. So if you then look at the operator mode on the right, this is a simplified panel that the user would see. So each of these inputs that are made available in the operator mode, each of these inputs correspond to regular inputs that a typical user would see in their user setup interface in the right-hand panel when you're setting up a typical case. But they've been brought here, consolidated to a simple panel with a few tabs to make it very easy for a user to set up a case. So you still have the ability to go into the full mode if you want to make other changes that aren't given in this simplified panel. But this does simplify it significantly for those that don't want the full mode. The input files that get exported are still the full input files, so nothing's changing on the solver side. So we've integrated ParaView into Converge Studio. As you're probably aware, ParaView is an open source software, and users are allowed to modify it and make changes to it. So we've done that and made a customized version that's simplified specifically for Converge, and we put this in Studio. So what you can see here is there's a new icon that shows up on the bottom of Converge Studio, and this opens up a new panel that you can load Converge output files directly. So we've created a tree that's very similar to what you'll see in ParaView, but we've simplified and removed a lot of the pieces and parts of Studio the pieces and parts of ParaView that are rather intimidating. Those of you that are new to ParaView, when you first open it up, it can be a little overwhelming. So we spent a bit of time doing the design here to just give you the features you want. So here are a few things I'm going to talk about. These are not currently available, but we anticipate these being available in a later version 4 release. So we're working on implementing basic CAD capability into Converge Studio. So this isn't going to be a full-blown CAD package, but we have licensed CAD capable libraries from Spatial, and we're working on implementing those to an interface in Converge Studio that will give you basic CAD capability. We're going to have a new feature coming later in version 4 that allows Converge to do 1D simulations directly in Converge. We have had the ability and still have the ability to interface with other 1D codes and have the two codes communicate with each other at those interfaces between 3D and 1D. The idea going forward here is to allow for the user to specify some portions of the domain that they import into Studio, specify some portions as 1D and some portions as 3D, and they'll be solved in the same Converge simulation, 1D and 3D together. So a big part of that is the setup in Studio, allowing the user to specify what portions of the domain are 1D, and then creating from the actual geometry that's imported into Studio, creating one-dimensional cells. So this won't be parts that are linked together like you would see in some 1D setups. This is an actual geometry that you import and then specify what parts of it are 1D, and you use the tools in Studio to set that up. So here's some other new features that will be coming out in Converge Studio. So we've got CGNS support for representing the geometry. Currently, we read your input geometry in a surface.dat format, which is our own ASCII format that we've come up with. Now you'll be able to import CGNS geometry directly, both representing the surface and representing intrinsic cell types if you're using an inlaid grid, We're going to expand that custom panel capability that we showed to give application-specific setup capabilities. So we can use that same custom panel capability to create our own application-specific wizards that hide unnecessary details. We're continuing to expand our inlaid and extrusion, boundary layer extrusion tools to make it easier for users to create inlaid meshes. And there's some improvement that's been made on the back end to speed up rendering of large geometries. So we made some changes to the I/O. Let's talk a little bit about output files. So as I mentioned, in Studio, you can import the surface geometry in CGNS format. We've also added the ability to output Converge post files in CGNS format. So we've had our own HDF5 format that's close to CGNS, but we've made some changes to it to make it actual CGNS format now. So those will still be able to be read into ParaView and TechPlot, but they should also be able to be read into any other CGNS capable post processor. We've added the ability to export your 3D output for a limited set of regions. So if you only care about what's happening in the cylinder, you can output for region 0 only, if region 0 is your cylinder. That'll allow you to output significantly less output, and it can save on your data storage. We've added surface output to ParaView Catalyst. So previously we've just had cell data output, but now you can output boundary information on the surface to ParaView Catalyst. We will soon have serial output capability. That will allow you to write output on only the head node if you're running a parallel simulation. So this can be beneficial if you don't have a high-speed parallel file system. You may have only the head node has access to the file system and each of the compute nodes don't. And so this will support that type of architecture setup. We've added the ability for the user to create their own custom output files. When I say output files here, I'm talking about the line plotting data. So those of you that run Converge are aware that we have a lot of output files, a lot of these text output files for doing line plotting. And sometimes you have to pull columns from many different files to put together into a single plot or single presentation. Well, you can specify ahead of time in Converge as an input file which columns from which files you want combined into one combined output file. So one example that's shown on the right here is we want to see the maximum pressure from all of the different streams. And for the different streams, the output files are written in each of their own directories. This allows you to pull the maximum pressure from a number of different streams and from a number of different thermo.outs into a single output file. So this is just one example, but this can facilitate some of the work that users have been doing in the past with scripts. You've had post-processing scripts to do this, and this allows you to do it as an input. We've made some changes to our UDF framework. So Going to version 3 from 2.x represented significant changes in our UDFs. And so there was quite a bit of effort that users had to put in updating their UDFs for version 3 and 3.1. So version 4 is going to have some tweaks to that UDF framework. This works better with our new back end. We've got a lot of changes that have been made in the back end. This works better with our back end. This will not represent a huge change to your UDFs. It should be on the order of 10 to 15 minutes per UDFs to change some of the headers at the top. You're not going to be changing your UDF, the main code in your UDF. All right, let's talk about changes that are coming up in chemistry and combustion. So we've added, it's called a surrogate fuel composition blender. So let's say you have some alternative fuel, or you have some fuel that you don't have a lot of data for yet. You know some of the physical properties for it, but you don't know everything, and you don't know how, you don't have all the data necessary to run it. Well, the surrogate blender tool allows the user to input. You can input some of the targets: molecular weight, hydrocarbon ratio, your oxygen to carbon ratios. You can give it octane or cetane number, ignition delay, anything that you do know about the fuel, you can input, and then you tell it which species you want to use for the composition. And then the surrogate fuel blender will try to match your targets by varying the composition, the species composition from the species that you're allowing, to try to match your targets. So this is a way to come up with a fuel composition if you don't have one already ahead of time, if you just have a fuel that you know some properties for. We've added more mechanism reduction and tuning capabilities in Converge 4. We've had capabilities for quite a while, but we've got some additional features here. So we've got utility to reduce and tune a mechanism based on 0D ignition delay, 1D flame speed. This enhances those that were available in version 3.1. You can also do mechanism tuning based on laminar flame speeds using our built-in premixed 1D solver. We've got this allows in Converge 4 for unlimited targets for the 0D and 1D reactors. We've also added sensitivity analysis for several of the 0D and 1D reactor types. So thickened flame model. So we've had thickened flame model has been available for LES in some pre-release versions in 3.1. We've had this available for a while. These become standard features in version 4. The idea with thickened flame is to give you a sufficient number of grid points inside the flame. We need at least 4 grid points inside the flame to get an accurate flame speed. For LES, we typically don't have enough of the turbulence viscosity to give us that flame thickness to give us the 4 points. And so what the thickened flame model does is it artificially thickens the flame to give you sufficient grid resolution, and it trades off the viscosity associated with that thickened flame for chemical reaction rates. So if you do the proper trade-off, you can still get the correct laminar flame speed by thickening the flame. So this is not something that we invented. This is something that's been around for some time and useful for LES. New for version 4 is thickened flame for RANs. The same principles that make thickened flame useful for LES also make it useful for RANs in situations where your laminar flame speeds are going to be very, very fast. You're going to have very thin flame thicknesses. So one example of that would be when you have hydrogen, when you have a hydrogen fuel. So hydrogen flame speeds can be much, much higher than what you typically have in other hydrocarbons. And so you can have turbulent flame thicknesses that are smaller than 1 millimeter. And resolving those, even in a RAN simulation, resolving those flame thicknesses becomes too expensive. So what's been developed is thickened flame for RANs, which makes using hydrogen and simulating hydrogen much more reasonable when you're using a thickened flame model. So here's just a quick example of that. So what we're showing here is the pressure trace for hydrogen combustion. What you're seeing is that we don't use any thickened flame, and we have 4 levels of AMR. This would be consistent with what you would see in a typical hydrocarbon fuel combustion. And you're seeing that you get basically a massive spike. In fact, the simulation was stopped here because it just all the combustion just went off instantaneously because with the hydrogen laminar flame speed is so fast. Okay, and then we've got 4 other plots that are shown here, and these are for different thickening factors. So you can see with the thickening factor of 16 and 3 levels of AMR, that's the blue curve that's a little bit off. That the combustion's a little slower from the other 3, but the last 3 with different thickening factors and levels of AMR, they all fall line on top of each other. On the right, showing the heat release rate for those examples. So this thickened flame, we're actually really excited about this. Hydrogen combustion is very popular these days, and we need a reliable way to simulate hydrogen combustion in engines. So the ECFM3Z model have been modified to allow nitrogen. So we've had general fuel definitions in the past where you specified your carbon, hydrogen, and oxygen species ratios, but it limits what you can simulate. We want to be able to simulate ammonia and hydrogen, so adding nitrogen to the general fuel definition allows us to do that. So we've got a new spark ignition model. So the conventional way of doing spark ignition is the user just specifies a region in between the electrodes of the spark plug where we would add a source, and that source was usually just fixed in that location. Well, we know that's not physical. That's not the way it really happens. And so we've worked with both Argonne National Lab and Southwest Research Institute to add a new spark model. And that spark model includes some of the best of both of those research efforts that we've been working on with Argonne and with Southwest Research. So the spark is modeled as a segmented line, and those lines are represented. You can see these squares here. It's essentially a particle type concept. So that line is represented by those particles, and then the sources are added where those particles are located. You can see as we have velocity interacting with the flow, it pushes the particles, and the sources are added where those particles are located. When they get too far away, there's a restrike. And then, so when you restrike, the line is initiated again between the electrodes and it's allowed to grow again. So there are some additional features. We got a secondary circuit model if you can put in the electrical information. There are several other things we're doing for combustion development. We're continuing to make improvements as part of the Computational Chemistry Consortium. So we're improving diesel and gasoline surrogates with that. Also, as part of the Computational Chemistry Consortium, we're looking at alternative fuels like hydrogen, ammonia, and methanol. One of the things that's not available yet, but will be soon, is the quasi-steady state species approximation. It allows us to have some of the species in your mechanism treated as pseudo-steady state, and so they're not actually transported. And that simplifies the number of species that are being transported to speed up your simulation. We're also looking at using artificial intelligence, specifically neural networks, to replace the direct chemistry solve. So we spent a lot of time working on steady state modeling. We'll talk briefly about what we have coming up in version 4 with that. So in the past, the steady state solver that's been available in Converge is a pseudo transient solver. So it uses a time marching to reach steady state. And we still have a DDT term on the left-hand side. So the convergence rates for a pseudo transient solver can be a little bit slower, resulting in longer run times. And sometimes the residuals don't converge very well. Now, the residuals not converging does not mean that it's not a well-posed problem. The residuals sometimes don't converge because when you're doing a transient type solution, you have some behavior in steady state solutions that is inherently transient and not steady state and continues to oscillate. And so that can make it difficult to get residuals to converge. That doesn't mean that it's an error, but we do need residuals to converge if we're going to take this steady state solver and use it in something like an adjoint solver for optimization. So we've been working on a new under relaxation based steady state solver. You may see an acronym URS, and that's what it stands for, is the under relaxation steady solver. So this does not have a time step specifically, but it uses under relaxation. Now that under relaxation that's used in place of a transient term still gives it somewhat of a transient behavior, but it's not transiently accurate. Now this is typically much faster than the pseudo-transient solver, and the residuals converge better. So I have a couple of examples to show here. So first one, this is straight pipe looking at liquid flow in a straight pipe. Now, the reason why this is interesting is because we've got very, very high aspect ratio cells on the boundaries, which are harder for convergence. So it's true that geometry that we're using to show the residuals converging is not a complicated geometry, but the setup itself with the high aspect ratio cells actually is a fairly difficult one for it to solve. And you can see on the right, we're showing residuals for mass and momentum and showing that they're following very nicely. Here's another example. This is an electric motor case with conjugate heat transfer. Now this one is using a new feature where we have cross-stream coupling. So this, you've got some metal parts in here, and you have some fluid parts. So when we're using the under relaxation steady solver, the solid parts and the fluid parts are converging at their own rate. So it's sort of like using a local time stepping approach. And this is much faster to solve than using the pseudo transient solver, which would take nearly a month to converge. Okay, so that's steady state examples with just flow. What about sprays? What about combustion? A lot of the steady state cases we want to simulate have spray and combustion. We'll talk briefly about what we're doing with steady state, but similar principles. I'll talk about what we're doing with sprays. Similar principles apply for combustion. And this is not currently available, but this is something that will be available soon in a later version 4 release. So Lagrangian spray framework is inherently unsteady. We've got random introduction of partials, and their interaction with turbulence model introduces some randomness. So that's inherently unsteady. So this unsteadiness causes the Eulerian field around the spray to also be unsteady. Now we want a steady solution because that's preferred for design exploration. As I mentioned, when we're using an adjoint type optimizer, we want to get a steady solution. Sorry, not just adjoint, but any DOE type of study that we're doing. So one approach is to just do simple averaging of all the sources to get us a steady solution. So instead of just taking the instantaneous values and going steady from the instantaneous, our sources that are introduced in each cell from the Lagrangian parcels represent a simple averaging of the sources at those locations. So here's an example of that. So this is a can combustor spray case, and we've got some of the setup parameters here. What you're seeing is we're injecting a spray at the left, flow is moving from left to right. So this is what the residuals look like if we run that case with using instantaneous sources. So with the instantaneous sources, our residuals fall to a certain point and then they flatten out. And of course they're going to flatten out because those sources are changing every cycle that we're running them. Those sources are introduced with randomness. Okay, so what happens now if we average those sources? So you can see the actual resulting temperature field on the left. If I use instantaneous sources or if I'm using average sources, that field looks very similar, but the residuals fall much nicer when we're doing source averaging. All right, let's talk a little bit about some improvements in embedding and adaptive mesh refinement. So these features are a result of requests that we've had from clients. We've had clients that have asked us, they said, hey, can I have my embedded region or my embedded shape move with a boundary? Let's say you wanted to put a box on a piston. You've got some phenomena you want to look at on top of your piston. Well, I want that box to move with the piston up and down. We didn't have that capability, but it's something that we've added. So here's moving with boundary. You can see I have 3 of the blades on this impeller have been given box embedding. And you can see that the embedding moves with those impellers. Here's the motion, prescribed motion. So you can see that I've got those same 3 boxes that I initialized around those impellers, but I've just given it a radial outward motion direction. So you can see they start by the impellers, and they're just given, each of them just given a translational direction. Okay, and then this is a combination of the two. So I've got one of my boxes that's given a prescribed motion, the other 2 move with the impellers. So we can also do something similar with adaptive mesh refinement. Okay, so in this impeller case, what I've done is I've given it 3 boxes, those same 3 boxes that you saw in the previous example around these 3 impellers, but we're not giving it fixed embedding at those locations. We're telling it AMR can exist in those locations. So that's giving us AMR on just those 3 impellers that we have the shapes around. And again, that's moving with those propeller blades. Okay, let's talk about some improvements in the solver. So in version 3.1 and in previous versions, we had Crank-Nicholson scheme was available only for momentum. So Crank-Nicholson is a mix between fully explicit and fully implicit. And Converge users know that we have a slider between implicit and explicit. We got a 0 to 1 that allows you to move from explicit to fully implicit. Crank-Nicholson would be a value of 0.5, where you're doing a direct average of the implicit and explicit. But that was only being applied to the momentum equation. So in Converge 4, Crank-Nicholson scheme is applied to the other transport equations as well. Density, momentum, energy, species transport are all done with a mix of implicit and explicit. So Crank-Nicholson is known to be second order accurate in time. That helps reduce numerical diffusion and give you more accurate results. You can get more accurate results with larger time steps than what you have with the first order, either implicit or explicit. All right, so here's a simple error analysis for a 1D wave in a channel. So what we're looking at on the right is we're looking at the L2 norm of the error for this analytical case that we simulated. And we can see for illustration here, we've got a first order line and we've got a second order line. And you can see with the implicit solution that it falls more or less on the same slope as the first order line. And then when we look at Crank-Nicholson, that the error falls more or less consistent with a second order line. Here's showing a 2D wave in a channel. So as this wave propagates, we're looking at different times. As this wave propagates through the channel, the wave should maintain its strength. And the strength is being illustrated with the red and the blue for the peaks and the valleys of the waves. So on the left is Crank-Nicholson, and you can see as we progress in time that the strength of those peaks and valleys maintains very consistent. When we're doing fully implicit, you can see that over time, the strength of the waves diminishes significantly. Again, that's the numerical viscosity that we get from using a fully implicit scheme that's destroying those waves. Okay, so we added in version 3.1 multiple streams. So rather than having all of your fluid information in a single stream with a single solver, in 3.1 we introduced the ability to have different fluids in different streams, solids in different streams, and have completely independent solver settings for those. That allows you to do a conjugate heat transfer simulation of your engine. You could have gas phase in the cylinder. You could have your piston and your liner and your head all in different streams of solids. And you could also have an incompressible liquid coolant that's in a separate stream. Well, that's great to have that capability, but it's not as useful if they all have to progress at the same time step. In that example I just gave, the gas phase, the combustion that takes place in the gas phase is going to drive the DT to be very small for accuracy, smaller than it would need to be if you're trying to get transient accuracy in your incompressible liquid stream, the cooling stream. It should be able to use much larger time steps and still maintain accuracy. So in version 4, we've expanded on the multi-stream capability to give different time steps for different streams. So transient time steps can progress at a time step that's appropriate for them. You can also have some portions of your domain. Some streams can be solved steady state. That example again that I gave of the conjugate heat transfer in an engine, we could make the solid stream steady state. So this accelerates the This accelerates your solution time significantly when you have these different, vastly different time steps required for different streams. So let's look at some examples of that. So what's being done here is when we use these different time steps, they're synchronized at the larger time step. So I can, essentially, I'm subcycling the streams that require a smaller time step. I'm subcycling them until they reach the time step at the higher time step streams. So in this example, I've got two streams, stream on the left, stream on the right. It's the same flow. They're connected with an interface, and flow is allowed to pass through that interface. But I'm using different turbulence models, and the different turbulence models are resulting in different time steps. So I'm synchronizing these streams every 20-3 seconds. And if you look, you can see that the flow goes through and you don't have any artifacts taking place at the stream in between here. Okay, here we have a vortex that's convecting between 3 different streams. So each stream is selecting its own time step. And you can imagine where I have the vortex, that stream that has the vortex is going to have a much smaller DT than the other 2 streams. And now look at the vortex as it passes through that stream interface. And you're going to see that there are some artifacts that we get. We can't, it's not possible to do this perfectly if you got different time steps and different streams. And you're going to see as it passes through that there are some numerical artifacts. But in general, it looks really good. And this allows you to get significant improvements in your runtimes. Okay, so here's looking at thermal runaway in a battery. So we've got flow going over a battery, and as it's heating up, you can see the temperature that we've got, the gas is heating up. Now the battery itself is also going to get hot. So you can see now where the heat source is being applied. You can see the battery is heating up. The battery is operating a much, much larger time step than the fluid surrounding it. We've added an electric potential solver. So this allows us to solve for batteries. We can do a better job of simulating batteries. So a quick example that was run with the batteries is we looked at different boundary conditions. Now in these results should all be the same. When looking at the electric potential field, it should be the same for all 3 of these, but we're applying one of them, it's voltage and voltage. Another one, we've got a current and a voltage. And then we've got a voltage and a current. So the voltage and current were chosen here such that the results should be the same. And you can see that they are. The resulting electric potential fields are the same. So using these capabilities, we can now simulate battery packs. And you can look at the evolution of a battery pack temperature field as the batteries discharge. So you can see as they start up, as they progress through time, you can see how the discharge is heating up the batteries. So there's some additional solver development that's been done. The image on the right here, this is just a eye candy. What you're looking at is a drone where we have the propeller spinning at different rates. And so that's why you can see the drone tipping and moving in funny directions. So we've got improved move surface and update grid performance. When you look at the time that's taken in different parts of the simulation, if you look in your log file, you'll see that in version 4, the amount of time spent in move surface and update grid should be significantly less. We've added support for ARM architecture. We're continuing to work on GPUs. There's not a lot that's going to be available in the initial version 4 release, but we are continuing to do GPUs. We're adding some artificial intelligence and machine learning for some models and for optimization. Doing more with inlaid grids. We got VOF improvements. We're linking structural solver with FSI, and I will show some examples of the VOF and the FSI. And then property enhancements for transcritical fluids. As we get into rockets, the fluid properties become very, very important. Let's talk briefly about some of the improvements that we're doing in FSI. So we've got fully implicit FSI. So we did have this available as a hidden in 3.1, now a standard feature in version 4. So for some scenarios, when you have similar densities between fluids and solids, the simulation can very easily go unstable if you have explicit coupling. So what we're looking at on the right here is we're looking at coupling of explicitly and implicitly for an object that is buoyant, that is moving up within a liquid. And what we're showing here, let's look specifically at the oscillation side to side here when you've got velocity side to side, and you can see we start getting these oscillations that go ballistic here on the explicit coupling. And if we're using implicit, they stay very, very clean. We've got a membrane model. So simulating a membrane can be very useful if you're doing things like blood flow through arteries, or if you're doing diaphragm pumps, parachutes, balloons, airbags. These are all examples where using a membrane can be useful. So there's some assumptions that go into this. What you're seeing on the right here is flow through a pipe, and you're seeing how the pressure waves are morphing the boundaries of the pipe. Here's a more extreme example. This is using a membrane model to show the filling of a balloon. So what you're seeing on the right here is this is the mass flow rate of air into the balloon. You can tell that whoever's blowing up this balloon here has a very consistent flow rate of his breath as he's blowing up the balloon. It makes for a pretty fun simulation result, though. It looks pretty cool. So we've also added a surface deformation model, and this is for modeling deposit and erosion. This is very useful for doing urea deposit for after treatment simulation. So what this model does is when you detect that you have deposits on your surface, the triangles that represent that surface are actually moved. They're moved consistent with the deposition. So if I have urea that's depositing, the surface triangles move up. And what you're looking at here is you're looking at the height of the surface. So as it changes from blue, that basically means we're adding deposits there by moving those triangles upward. So this allows you to more accurately predict the flow when those deposits exist. So here's coupling between CONVERGE and Abacus. You're seeing the CONVERGE results on the bottom right here. We have a disc type reed valve. The flow is allowed to move up and down as this disc. You're seeing a cross section across the disc as the disc moves up and down. And you can see the flow leaving but not entering. And then those forces that are predicted from the fluid dynamics simulation are then applied in Abacus. So you can see what that does in Abacus. So we got a few improvements I want to hit briefly in multi-phase. So we've got an improved boiling model. This was developed in conjunction with IFPEN, which gives you a better representation of the different boiling regimes. And this is useful for accurate urea deposit modeling. One of the test cases that was run for testing this new model is the Lauer experiment that was done. And so this looks at, we got wall temperature. We also have, we can look at liquid and solid that exist on the plate. We have on the left here, this is the image, and you can see our liquid film and our solid deposits. And you can see that there is pretty good correlation here, specifically the solid deposits where you've got the brightest, and you can see that we're doing a pretty good job of matching that. We've also added some new cavitation models. These are homogeneous mixture-based cavitation models. Some of them have benefits for specific applications, and so that's why we have multiple models in here. There isn't one that's universally the best. We got a couple example cases we're done. We ran the Winkelhofer case. This is with the Schneider and Sauer model, and then a hydrofoil cavitation with the Singhal model. We've also added a drift flux model. So this allows us to look at multiple phases through porous media. This can be useful for simulating fuel cells. So here's an oil drainage example. So in this example, we've got different permeability in different blocks. And so this is the setup that you're seeing in the upper right here. And you can see the different permeabilities for these different blocks. So we have water moving in, and the domain initially has oil in it. And as the water moves in, it displaces the oil. So these are other results from another code, for example. I'm going to run that movie one more time here. So you can see as the flow moves in, it permeates at different rates based on the permeability. Agrees very well with the simulation from the open foam. So additional multi-phase features that we've got in there, we've got a deposit solidification model, temperature dependent contact resistance and interface boundaries. We've continued to improve ELSA, and we've added there are two features that were available as UDF only that are standard features. That's the ELMO model that was developed as part of the Spray and Combustion Consortium. And also the swirl cone angle predictor from the same SCC consortium. We have boundary specific wall interaction, so I can set boundaries to behave differently when they're struck by parcels. And we were also adding gas parcels. That's not available initially in this first version 4 release, but will be available soon. Well, thanks for your attention, Scott.
Yeah.
Time back over to you.